Trust me, the only thing hard about this algorithm is how you pronounce it. Even I had skipped it the first time when I was learning about graphs. Well, Dijkstra's algorithm is actually very essential because it involves finding the shortest path between two neighbors when you're given a graph. So you can easily understand that this algorithm will be very important in some real life applications. Also, the good part is that it works on a greedy approach. So let's see what we can do about it. Hello friends, welcome back to my channel. First, we will take up a sample graph and understand what do you mean by the shortest distance. Going forward, we will use the Dijkstra's algorithm to derive these shortest paths. We will do a step-by-step demo so that you can actually see how this shortest path is being calculated. After that, as usual, we'll also do a dry run of the code so that you can understand and visualize how all of this actually works in action. Without further ado, let's get started. Let us say you have this graph in front of you. So you can assume it that all of these nodes, these are different cities on a map. And these are the paths that are connecting these cities. So between two cities, you have a certain distance, right? Now, the problem is that, okay, let us say you're starting from city number A and you have to reach city number F. Then what is the minimum distance in which you can make this trip happen? So definitely you can take multiple paths, right? You can go like this, then this, or you can go to C, then B, then this, or there are some crazy paths possible as well, right? Suppose you can go to C, then you can go to B, then you can go to D, and then you can go to F. So what I mean is that there are a lot of different paths possible. And if I ask you, okay, what is the minimum length? Then the brute force way will be that, okay, you find out all the different paths and then tell me that yes, this is the smallest path. But if you think about it, what about a very huge map or a very huge graph? You cannot go on calculating all of these distances, right? So certainly we need an efficient way how you can go about finding out this minimum path. So one way that you can do is that is the Dijkstra's algorithm. So what we basically do is, let us say you have this graph in front of you. And now you have to find out the distance between this particular node and this particular node. And it has to be minimum. What you do is you have to start somewhere. You can say that, okay, I am starting at this particular node. So I will mark this distance as 0. Because if you have to start at A and then reach at A again, you don't have to travel anywhere, right? So the minimum distance between node A and node A will be 0, correct? Now, from node A, you can go to node C and you can go to node B. And what are the length of these two paths? They are 4 each, right? So what I will do is, I will write down 4 in both of these nodes, correct? So basically what I have now done is, I have traversed these two paths. What happens now? You're done with node A, right? Now, if you look at node C, you can also go to node B from node C, right? This is also one path. So your total path becomes A to C and then to B. So that gives you 4 plus 2 and that is 6. So if I go directly from A to B, then the length is 4. But if I go to C, then I go to B, then the length is 6. So this is what we are keeping a track of. So if you see 4 plus 2, that is 6. And that is greater than 4. So you do not need to update this value. We know that this is the minimum length required to reach from node A to node B, right? So this part is now done. You don't have to worry about it. Now moving ahead, where can you go from node B? From node B, you can go to D, you can go to F, and then you can go to E. You have already traveled a distance of 4. If you do 4 plus 3, then you get 7. So I will write down a 7 over here. If you travel 4 plus 6, then you get 10. So I will write down 10 over here. And if you travel 4 plus 1, that is 5. So I will write down 5 over here. So what did I do over here? I have explored all the different options where I can go to from node number B. So this is telling me right now that okay, I can reach this last node with a length of 10. But it may not be the minimum because we still have these two remaining paths to explore, correct? So how do you go about doing it? If you look at it, if I am trying to go to node F from this path, right? Up till here, the length was 7, right? We have recorded it, 4 plus 3. So if I have to take this path, what will be the length? 7 plus 2, and that is 9. 9 is less than 10, correct? So it means that this is a shorter path, correct? So what I will do is, I will simply update this value. So what is basically happening is, on the left, I am determining that, okay, with all of these covered edges, what is the minimum distance required to reach each of the nodes in the graph, right? You are not done yet. You still have one edge remaining. So if you have to reach node number F, you can utilize this E number node as well, right? And to reach here, the total length was 5. So what you can do is, you can come here and then do 5 plus 3 and then also reach F, correct? So 5 plus 3 is 8 and 8 is even less than 9. So what we can do is, we can simply replace this value. This final graph, this is telling me that what is the minimum distance that you will need to travel to each of the node. So if you have to travel from node A to node F, then the minimum distance is 8. And this distance can be derived if you go via this path. So this was the minimum distance, right? Now you can think why Dijkstra's algorithm is very, very important. This is literally an entire map, right? And all of these are cities. You have to reach from city A to city F. Then what path should you take? This is the shortest path, right? And this is how we derive it. So this is the basic crux of Dijkstra's algorithm. You find out the shortest path between two nodes in the graph, correct? But over here, we were just going off with the idea of the Dijkstra's algorithm. We were at a node and then we were exploring all of the possibilities where we can go. How do you do it algorithmically? Suppose you have to write a program for it. Then what do you do? Once again, I have this graph over here with me. And we will try to apply the Dijkstra's algorithm. In Dijkstra's algorithm, we also take the help of a priority queue. Because when we are picking which edge to go to, we apply the greedy approach and we try to pick the edge which has the minimum weight. Because we assume that if I have to reach from point A to point B, then all the distances between these 2 points, they are also the minimum. What do I mean by that? For example, I have a city A over here and then I have a city D over here. And let us assume that the minimum path between these two cities looks something like this. Dijkstra's algorithm says that for this path to be the shortest, then if there are any other nodes in here as well, for example, if I have city B here and if I have city C here, then this shortest path will also include the shortest path between nodes B and C also. It cannot be possible that there is some other shortest path between node B and C, but the shortest path between A and D will look something like this. That cannot be true. Because think about it. If there was a shorter path between node B and C, then the shortest path between A and D will also include that shorter path, right? That is why we use a priority queue and we will try to pick the edges with the minimum weight at every instance. You will see what do I mean by that. Over here, I also have a map data structure that is just storing the distance between node A to every other node in the graph. Because for our current problem, A is the source node, correct? If your source node changes, then all of these distances will also change, right? So this is very specific. So currently, I am calculating the distance between node A to itself. That is a starting point, right? And I can simply write down a 0 over here because the distance between node to itself will always be 0, right? Now you have to proceed ahead. So first of all, what we can do is we can assume all these distances to be infinity. It simply means that I am assuming that I cannot even reach these nodes. This is the maximum distance. As we go ahead and proceed our loop, we will update these values. So what do we do over here? First of all, I am at node A. And now I have two edges. That is to B and to node C. Since it is a priority queue, it is supposed to be inserted in the ascending order of their weight. But since they have the same weights, they will just get inserted in any order. I have now inserted these edges, and now you will run a while loop until your queue is completely empty. What do? You will pop out this edge, and this edge is connecting node A and node B. What does this tell you? This tells you that to reach node B, there is a weight of 4. And where are you starting? You are starting from node A, right? So 0 plus 4, that gives you 4, correct? And 4 is less than infinity. So we can go ahead and update this value. Now look at all the neighboring edges of this particular node. I have all of these edges, right? And they will be inserted in your priority queue in the order of their weights. So I have these particular edges. So all the edges are now in your priority queue in the ascending order. You can see edge 3 is over here, edge 6 is over here, edge 1 is over here, edge 2 is here, right? You have all these edges. And once again, what you're going to do is you will start to pop an edge. As soon as you pop an edge, I am looking at this particular edge, right? So I am visiting node E. And to visit node E, what is the distance? You will look in your map. To reach B, what was your distance? Your distance was 4. So to reach E, the distance will be 4 plus of 1. And that gives me 5. So 5 is less than infinity. So I can update this value. You will now add all the edges that node E has to your priority queue. I have one edge over here, right? That has the weight 3. So this is also gonna get added to your priority queue. To proceed ahead, we will pop out an element from the priority queue, and I am looking at this particular edge. It has the weight of 2. This is the edge I am referring to. And this edge is connecting node C, right? So what we will do is we will try to populate our value for this particular node. To reach node B, my distance was 4 and 4 plus 2, that is a 6. So I am reaching node C with a length of 6, right? 6 is less than infinity. So we can safely update this value. What edges does C have? C already has an edge 4 that is already in your priority queue, right? So you don't have to do anything. Once again, pop an element. I pop an edge and I get the edge 3. So this edge could be anyone. This edge could be this or it could be this one. Let us say I am getting this particular edge right now. So this edge, I am reaching node number D over here with this edge. And what is the total distance? To reach B, the length was 4, 4 plus 3, and that is a 7. So you will compare, is 7 less than infinity? Yes. So I can update this value. Look at the edges of this node D. It has an edge 2. And since the edge weight is less, it will go in your priority queue at the very beginning. This is how you keep on proceeding ahead. Once again, pop an element. So you get this particular edge. And which node are you reaching? You are reaching node F. And what is the weight? You start from D, so the length is 7, and then plus 2. So 7 plus 2, and that gives you a 9. 9 is less than infinity. So I can go ahead and update this value. We will look at the edges of F. They are 6 and 3. And they are already in your priority queue. So don't do anything about it. Pop an element once again. This time you get this particular edge, right? To reach E, the length was 5, correct? And 5 plus 3, that is a 8. And where do you reach? You reach at node F. So once again, you will compare, is 8 less than 9? Yes. So now, once again, you can update your value. So you see how we are covering all of the edges. This will sum up everything. Now pop out once again. You get the edge 4. And we are talking about this particular edge, right? The source is A and the destination is C. So to reach A, the distance was already 0, right? And 0 plus 4, you will reach C. So 0 plus 4 is 4, which is less than 6. So I can update this value. I am left with one remaining edge. I will now pop it out. And what is this telling me? The source is B and the destination is F. So to reach B, the distance was 4. 4 plus 6, that is 10. You reach F. Check the value. 10 is greater than 8. We want the minimum value, right? So you do not have to update it. So what did we just do? We covered all of our edges, and now in this map, we have the information that if you start from node A, these are all the minimum distances that will be needed to reach each of the node in your graph. And this is the Dijkstra's algorithm. Let us now quickly do a dry run of the code to see how it works in action. On the left side of your screen, you will have the complete code to implement the Dijkstra's algorithm. And on the right, once again, I have a sample graph. And notice that I will pass in the source as my parameter of the function. So my source is this node A. So based upon this, our calculations will proceed ahead. So what is the first thing that we do? First of all, we will create our map, right? That will store all the distances. So I am creating an array that is having all the values as infinite right now. Next, what we do is we create a priority queue. And in this priority queue, all the edges will be sorted automatically in the ascending order of their weights. To initialize things, if you remember, we had the source distance as 0. So I just have that, okay, the distance of the source is 0. So I'm gonna update this value. And to get things rolling, I just add a dummy graph edge where the source and the destination both are your first node and it has a weight of 0. So I know that when I'm popping elements, I have a starting point. The next part is where you start your while loop. And you will run this while loop until your priority queue is completely empty. What do? You will pop out an element and then look at all the edges. So I have 2 edges right now. And then for each of the edge, you will get its weight and then try to find out if it is less than what I already have over here. If yes, you are gonna update this value. Otherwise, you just leave it as is. And then once again, you just take all the edges of the current vertex and add it to your priority queue. So this is how this loop will continue to run on, and at the very end, you will have your all the shortest paths in this entire array. The time complexity of this algorithm is order of E log V. E is the number of edges and V are the number of vertices. Log V because at every step we will be able to eliminate some of the vertices which have a greater distance. The space complexity of this algorithm is order of V because you need that extra space to store all the distances between the source node and the destination node. I hope I was able to give you a good understanding about how the Dijkstra's algorithm actually works. As per my final thoughts, I just want to say that this is a very essential concept when it comes to problems on graphs because it has a lot of real world applications. Think about it. When you are navigating in a map, let us say your GPS system, this uses the Dijkstra's algorithm to find out the shortest path to reach your destination. Similarly, it is also used by internet service providers to actually route your data or traffic very efficiently in the minimum possible time. So, this concept has a lot of different applications. And as usual with all the other concepts of graphs, the best way that you can solidify your concept is just take out a sheet of paper and draw some random graphs. Try to find out the shortest path from any source to any destination. Trust me, this will really clear up how the Dijkstra's algorithm actually works. And then you can go on to solve more problems on it. So, while going throughout the video, did you face any problems? Or do you have any other method in mind by which you can implement this algorithm? Tell me everything in the comment section below and I would love to discuss all of it with you. As a reminder, if you found this video helpful, please do consider subscribing to my channel and share this video with your friends. This motivates me to make more and more such videos where I can simplify programming for you. Also, a huge shout out to all the members who support my channel. You guys really keep me going. And remember, you also get priority reply to your comments. With this video, we have covered most of the solid concepts that you need on a graph data structure. And now we will be moving on to solving more and more problems. So until next time, see ya.